Our guest today is Professor Christopher Batten, who is an assistant professor in electrical and computer engineering here at Cornell. Professor Batten has won multiple Young Investigator Awards for his research in computer architecture, as well as the top awards in the College of Engineering for his teaching and advising of students. And Chris, we're very happy that you can come by today.
Glad to be here.
So I'd like to start by exploring a bit your own personal story as to how you got to where you are today. So I'm kind of interested in hearing, how you got interested in electrical and computer engineering, computer architecture. So did you have an interest in computers at a young age?
I did. My first computer was Apple IIGS, and I remember my uncle sent me a stack of books, and I remember fondly writing out long basic programs on a piece of paper and then typing them into the computer. But my first experiences kind of more seriously with science and engineering were in high school. And so two experiences I remember are, one was having the opportunity to take advantage of a magnet school for technology, more specifically robotics, in my city. So high school students from across the city would go to this one specific high school for coursework in technology and robotics. And the robotics program was pretty remarkable in the sense it was largely student-driven. So there was a textbook, and students were encouraged to pick chapters they were interested in and basically learn the material and then give lectures to the rest of the class. And there were projects throughout the semester that students could independently work on. And one that I remember was a project with a robotic arm and a vision system, and working very hard on a program to analyze shapes coming down a conveyor belt and do pick and place. So stack all the triangles in one stack, track all the circles in another stack. And I loved how it was interdisciplinary. You were working with a robotic arm, you were doing hardware, you were doing software, and I really loved that. Another experience in high school which got me interested in math and science was the two-year science fair project, and it involved experimenting with paramecium, a type of bacteria. And paramecium have interesting behaviors in terms of responding to their environment. So for example, they don't like very hot temperature, and they don't like very acidic pHs. And so I asked the question, well, what happens if you put them in a conundrum? What happens if you put paramecium in a little trough and you make one side pretty hot, but the other side pretty acidic? Like, how hot does it have to be in order for the paramecium to change their mind in terms of temperature? And it was a two-year project. I did lots of experiments, and it was really fun. But the best part was Virginia, where I grew up, has the Virginia Junior Academy of Science, which is held in collaboration with the Virginia Academy of Science. And the Virginia Academy of Science, that's the real deal. Like, scientists from all over the state get together and talk about their work and make presentations. And in parallel, the Virginia Junior Academy of Science, high school students get up and they present their work. So it's not really standing in front of a poster, you actually present. And if you win, and I didn't win the first year, but I won the second year, you get what I thought was the grand prize, which is you get to present your work to real scientists. And so I got up and I talked about my paramecium experiments to 10 or 15 real biologists, and they thought it was moderately interesting, and I thought that was a fantastic experience. And that got me excited about math and science, and I particularly like the computer programming part. I did a little bit of that in the paramecium experiments and a lot of that in the robotics program. So I went to the University of Virginia. I was going to major in CS. That's what I wanted to do. I wanted to learn about computer science and programming and algorithms and all this. And that was my game plan until I took my first course in computer engineering in my sophomore year. And all of a sudden, a whole other world opened up where you could do and study hardware and software. So really get a broad view of the entire computing stack.
So that course was digital logic,
right.
Organization?
Yep. It was an introductory digital logic course where you learned about the basics of digital logic and a little bit about computer organization. And all of a sudden now I realized that I could study not just software, but software and hardware. And so I switched majors to EE. That was where computer engineering was at the University of Virginia, where I did my undergraduate work. And it was definitely the right choice for me. And as part of the University of Virginia's undergraduate curriculum, all engineering undergraduates have to do an undergraduate thesis. So I immediately knew I wanted to do my thesis with both a hardware and software advisor. So I worked with Professor Ron Williams in the EE department and Professor Paul Reynolds in the CS department on, I forget the details, it was like a fault-tolerant network, and I was looking at the hardware aspects and trying to kind of understand some of the strengths and weaknesses of a specific design they had. And again, the highlight was really having an opportunity to present my work in the Rotunda. So I'm not sure if you're familiar with the University of Virginia. Yep. Thomas Jefferson, very famous. The Rotunda is the center of the university. Used to be Thomas Jefferson's library. And it was just an amazing experience to get up in that in that hallowed space and present my research. And those experiences really motivate me to pursue graduate school, along with one of my mentors there, Professor Mercer Stan, who encouraged me to pursue a PhD. And I knew right away that I wanted to go to a university where I could do research on both hardware and software. And that's ultimately what I was able to do. It's still what I love, and it's still what I teach and research.
Now, when you did your PhD, you were able to actually work on some real chips.
That's
you
right.
You actually did real chip design. You
That's right.
produced the chip. And could you talk a little bit about that experience?
Sure. So, you know, kind of following off what I just said, I was really excited about doing software, hardware, but also building a simple prototype. And so as part of my PhD work, we came up with some interesting ideas for new ways to execute programs efficiently. We did some modeling. The results seemed very promising. And the specific group I was working in, along with my research advisor, Professor Krista Sanovich, had the resources and motivation to actually encourage us to fabricate a small test chip to illustrate these ideas. And so myself, along with my colleague, Ronnie Krasinski, who was the lead architect on the project, he worked on the execution engine, I worked on the memory system. We taped out this small chip, and it was fantastic to do modeling, then get the chip back. First of all, it worked, and second of all, the results with the actual chip were very promising. And that was definitely one of the highlights of my graduate career.
So in your research now, you're dealing with somewhat about the layers of abstraction. So in this course, we talk about the layers of abstraction, and we think of them in kind of big chunks like digital design, computer organization, and then we break this up into microarchitecture, instruction set architecture. Now, within microarchitecture, there are layers of abstraction as well, right? So can you talk a little bit about those detailed layers of abstraction in microarchitecture?
Sure. So, you know, I definitely agree with you that one of the best ways to understand computer systems is by thinking about these layers of abstraction. And beneath microarchitecture, once we have a microarchitecture at a high level, we might want to refine that down to, for example, the register transfer level. And at this level of design, now we're starting to talk about the actual bits, we're starting to talk about the state, how we move state between registers, and then we might refine it down to the detailed gate level. So we think more about the actual specific adder design and you know, the specific memory structures, and then we'll refine it down to the circuit level. So there we're thinking more about specific logic styles, how we actually use the transistors. And once we get to the circuit level, then of course beneath that we have devices, and at the very bottom we have physics, technology, the electrons, silicon. And at least in my opinion, I think one of the beautiful opportunities and challenges with computer engineering is about these layers of abstraction. So on one hand, they're a tremendous asset. It allows us to focus on one layer of abstraction, and as long as we understand the interfaces to the layers above and below us, we can do really amazing things. And this is one reason we can build 10 billion transistor chips, and they work. And they're high performance and energy efficient. But on the other hand, abstractions create challenges, because I don't necessarily know what's beneath me in the details, and I might miss opportunities for improved performance or energy efficiency.
So if you're at this high level here, you need to understand the timing, for instance, right?
Exactly.
The implications of working at this level and the lower level timing and power and area and those types of things.
Exactly. So those are great examples. So at the microarchitectural level, I can really understand the cycle level behavior. So how many cycles does it take for an instruction to execute on a pipeline? How many cycles does it take for a memory request to access a cache? But there are other metrics which are as important. For example, like you said, area. So how much area does a specific design take? Or energy. How much work does it take to do a specific transaction? Or timing. What is the cycle time? It's hard to understand those at a very high level abstraction. The best way to understand those is by moving down the stack. And it's particularly exciting when we can find opportunities to create cross-layer optimization. And so that's a lot of what I look at in my research. So places where we can optimize across the stack, and that's exciting in and of itself, but what's even better is if we can create new abstractions, the abstractions for tomorrow, which will still enable the benefits without giving up too much of the opportunities.
So you're talking about actually changing the well-known, well-followed abstractions that we have today to something that's a little bit different.
Right. So as a quick aside, so I was a graduate student for a relatively long time. And in the middle of my graduate career, I actually had a crisis of heart and I think I was going to go be a molecular biologist. The field was really hampered almost by these abstractions. In the research community, there was an emphasis on, are you working above the instruction set architecture, or are you working below the instruction set architecture? But if you want to change the instruction set architecture, people would be a little bit apprehensive because industry was not willing to kind of allow like radical changes to the instruction set architecture. And I found that a little discouraging because I thought one of the most interesting things were when we break down the instruction set architecture, add new instructions. And yes, maybe industry doesn't adopt them, but I think it created really interesting opportunities for research. But this is right before maybe the transition to multi-core, the trend towards energy and power becoming absolutely dominating constraints. And within a year, around 2004, 2005, all of a sudden everybody was talking about this kind of cross-layer changes, changing the instruction set, radical new instruction sets. And the field all of a sudden became very exciting, very, very fast. And so that's right. So my research looks at, can we add new instructions and get good benefits? But we always are trying to be careful. We don't want to change it too much. Can we just add a couple new instructions and get a very, very big benefit? And what are the right instructions to add? What are the right abstractions to introduce?
So you take this, what you call a vertically integrated approach. So
Right.
you're able to explore the instruction set, for instance, adding a couple new instructions that might potentially make our design faster. And then you have a methodology for seeing how that impact will be across all the different layers.
That's right. And so what's really challenging is, it's easy to say we'll change the instruction set, we'll add some new instructions. But how's your application, which is written at a high level, going to use those instructions? Well, I could do some research where I write all my programs in assembly. Like in the course, you do a lot of assembly programming. But if we want to look at really challenging applications, I'm not going to be able to do that with doing hand-coded assembly. That means we need a compiler, which takes a high-level language description and compiles it to assembly. Well, the standard compilers don't know about my new instructions. I just invented them. So does that mean I need to invent new compilers? Yeah. I mean, maybe not from scratch, and maybe we can take existing compilers and make small changes, which is what we try to do. And that's another reason why it can be quite challenging. And then you change the instruction set, and the question is like, well, why? And so then you have to work down the stack. You have to understand what are the implications of the microarchitecture, but also, does this cause unforeseen consequences in the register transfer level, the gate level, the circuits, or are there kind of interesting unforeseen benefits from kind of changing this abstraction?
So you mentioned energy efficiency, power, and this being a big issue. And of course, this is a huge issue when we have a smartphone, because we want to get performance, but we don't want our battery to last only 3 hours. So this is a bit of a conundrum for designers. Like, how do we make fast designs yet make them energy efficient? So you've done a lot of work in this area. Can you talk about kind of the techniques that designers use to get energy efficiency as well as high performance?
Sure. But I think one point to make before I say that is about the difference between energy, performance, and power, because often these get confused.
Yep.
So energy is really how much work it takes to do some task. So for example, how much work does it take to process a video frame? Whereas power is the rate change of energy. So what's the rate at which I'm consuming energy? And it's really easy to make low power processors. You just make them really slow. But often we want both. We want high energy efficiency, so low energy, and also high performance. And that's the real challenge. For a long time, computer architecture was really a game of trade-offs where you would increase the performance, but you would add complexity, which meant you were doing more work and more energy. So it was this constant tension where, yes, I'm going to get more performance, but it's going to use more energy. But in the last decade, that's no longer good enough, because now we need to understand how we can increase performance at the same energy and try to stay under some type of power constraint. And so when we think about energy and power, we also need to think about what the constraints are. So they constrain very different parts of our system. So energy barely constrains things like your electricity bill or the size of your battery, whereas power constrains things like heat. So how hot does your cell phone get? And once we have an understanding of the difference between energy and power, then we can think more about ways to tackle them. So there's many ways you can tackle improving energy efficiency at different layers of the stack. So for example, at the microarchitecture level, I could move to a simpler design. So maybe instead of a set associative cache or fully associative cache, a direct map cache would be more energy efficient. Now I give up something in terms of performance, and I have to understand those trade-offs. But looking at simpler microarchitectures is one way you can make things use less energy. At the gate level, we can do things like clock gating. So in clock gating, if I have a state element, like a flip-flop, and if I think about that flip-flop, every cycle the clock is toggling. But what if the flip-flop's not doing anything? Well, then that basically means we're wasting work. And for wasting work, we're wasting energy.
Now, I've said in the course that in a synchronous design, you always have the clock running.
That's right.
Right? It's running, you power it up, it's running all the time. So you're saying, Ashley, we won't have that to be the case all the time.
So that's the great abstraction. But in reality, any modern design, if the clock was running all the time to every flip-flop, it would consume significantly more energy and power. So instead what we'll do is we'll try to identify pieces of the chip where we can gate the clock, essentially stop the clock. And we do this at an amazingly fine granularity. On a cycle-by-cycle basis, we can make local decisions about whether or not to enable or disable the clock. Now that's the clock signal, but you can do something similar for the data signal. So for example, if in my processor pipeline I have a multiplier, an adder, a shifter, but any given instruction might just use one of those components. If I'm not careful, all those components will be doing work that's wasted. So with data gating, what we'll do is essentially we'll gate the data lines and make them all 0 for the units which I'm not using. And in this way, they don't consume energy, they don't do work, and that can make it more energy efficient.
Now you might do this in the register file too. So for
Absolutely.
instance, if I have a instruction where I really don't need to read the register file, I won't do that.
Absolutely, that's right. And there's all kinds of really interesting implications of that. Because, for example, how do I know I don't need to use the register file? Well, I might need to decode the instruction to know whether I need to use the register file. Now, all of a sudden, two tasks, which I may have been able to do in parallel, I now need to do in sequence, and this might impact my overall number of cycles to execute a program. So there's always interesting trade-offs that you can start to see ripple up and down the stack. And at the circuit level, one of the key knobs we have is voltage. So for example, we can run specific parts of our chip at different voltages to make them more energy efficient. And this is a particularly powerful knob because energy is proportional to the square of the voltage. In other words, if I slow down my system by lowering the voltage, I can get a significantly more bigger benefit in terms of energy efficiency. And this has actually become the #1 way modern microprocessors, from smartphones to high-performance computers, manage the tension between performance and energy, is that they will adaptively scale the voltage in response to demand. So for example, let's say I'm decoding a DVD on my laptop. I only need a frame once every 30 seconds. And if I have a very high-performance processor, it might work so fast and so hard that it could basically, run my video at 60 frames a second. But I don't want to watch the video at 60 frames a second. I want to watch it at 30 frames a second. So we can scale down the voltage, slow down the video decoding. It'll be more energy efficient, yet to me as the user, I don't even notice.
Now this assumes you have some way of determining the correct rate, right?
Absolutely.
So you need to be able to do some kind of monitoring or detection.
Up and down the stack, that's exactly right. So either I need to, maybe my application, I instrument my application. So my DVD decoding application has specific hooks to tell the hardware, hey, I only need to decode a frame 30 frames a second. You're welcome to work harder than you need to, but you're just wasting work. Or maybe we don't want to expose that to the software, in which case maybe we try to engineer sophisticated hardware mechanisms to almost predict what the required performance is. And there's really a wealth of different techniques in order to leverage what's called dynamic voltage and frequency scaling across the stack. And it's a great example of how tackling energy and power really requires a cross-layer approach.
Right. Now, if I have a smartphone, a typical smartphone, is it doing this voltage scaling? Is it doing this clock gating? Is it doing all these things you just talked about?
Absolutely. Modern smartphones will take advantage of these techniques along with a wealth of other techniques to try to optimize energy and power because it has a real benefit to the consumer. If I have to charge up my phone twice a day, my phone is not going to be as useful if I have to charge up once a week. So another great cross-layer approach to improving energy efficiency is specialization. And this is a particularly hot topic in the research community right now. So the idea here is if I really want to decode a DVD and get the best performance at the least energy, the way to do that is to create a specialized piece of hardware whose whole job is just to decode DVDs. And then I can get much better energy efficiency, much better performance than I could running a software DVD decoder on a processor. And of course the problem is that's specialized for MPEG-2. We're using H.264 now. We have a new video standard, and that awesome accelerator, which is so energy efficient and high performance, can do nothing to help me with these new video standards. So this tension between flexibility and specialization, I personally think is one of the grand challenges in the field. In the sense of how do we navigate this tension between general, less efficient architectures and specialized, more efficient architectures. And it's one thing that I'm looking at my research, but definitely across the community, many people are tackling this from a variety of different ways.
Now, if you have specialization, that implies that you have enough room on a chip
yes.
to put in all of these specialized functions that, at any given time, most of them are not being used.
That's right.
They're just being kind of wasted.
That's right. And so specialization makes less sense if area is a very, very tight constraint, because then I want to use every single transistor for as many purposes as possible. But we're kind of in this interesting domain right now where the number of transistors we can put on a chip far exceeds how many transistors we can actively use at any given time. So we need to think about creative ways to use those transistors. And so like you said, one idea is to use specialization. Yes, I've got a piece of my chip which I only use 10% of the time. But I couldn't really put anything else there anyways, because I don't have enough power to be able to keep it operating. And so there's this, this term in the community called dark silicon. The idea that if I look at a chip right now, a large portion of the chip is essentially dark, is not being used at any given time. And that changes, it fundamentally changes the way you build systems. All of a sudden now specialization becomes more attractive. It doesn't need to be quite as flexible as it used to be. But can it be so specialized I can only use it, once every couple days? It can be that? No, it needs to be somewhat flexible. And so kind of navigating that tension is one of the really interesting research questions going on right now.
Now, we already have specialization on a system on chip of the smartphone, right? Because we have a video processor, an audio processor, and we have the general purpose apps processor. And in a very good example of specialization is a graphics processing unit, or GPU.
That's right.
And that's one of the reasons we get such eye-popping graphics out of our smartphones. So we talk a lot in the course about the organization of it's called the apps processor, the general purpose processor. So how is a GPU different in terms of its organization and how it exploits parallelism?
Sure.
Does it use instruction level parallelism, thread level parallelism, data level parallelism? So how does it work?
So I think in the course you've been talking about multi-core as well, right? So having multiple cores.
That's right.
So let's imagine we want to build a house, and let's say we have a bunch of carpenters. There's a couple different ways we could organize those carpenters. So multi-core processor is essentially the idea that we get our four contractors together, our builders together at the beginning of the day, and we say and they kind of collaborate together, and they say, oh, I'm going to work a little bit on the roof, I'm going to work a little bit on the floor, you're going to work a little bit on the walls, you're going to do the bathroom. And then they go off and they work on their piece of the house, and at the end of the day, they come back together and see how they did. So that's one way to exploit parallelism. And so this is very much kind of coarse-grained parallelism where each carpenter is doing a very different job.
You can think of each of those jobs as a thread.
Exactly. So each of those jobs is a thread, and they're doing kind of different things on different parts of the house at the same time. So GPUs exploit a fundamentally different type of parallelism called data parallelism. And the analogy would be, let's say I have a foreman who shows up along with my 4 carpenters. And the foreman's job is to organize these 4 carpenters. And the foreman says, you know what, we're not going to do 4 different things. We're just going to focus on the walls. I want all 4 of you to do the same thing on each of the 4 walls together. And so the foreman orchestrates the carpenters to essentially do similar tasks on different part of the house at the same time. Once they finish the walls, then they'll move on to the roof. Then they'll move on to the floor. One of the benefits of exploiting data parallelism is I could add another 4 carpenters, and they would just slip right in lockstep, do what the foreman says, and I could potentially complete the house much faster. Whereas if I have 4 carpenters that are all kind of doing their own thing, and I give it 4 more carpenters, and they have to kind of organize and synchronize and communicate, it's not clear that that's actually going to add that much benefit. So the key to graphics processors is that they exploit data level processing in the sense of they have a control processor, which is in charge of a lot of engines, which all operate in lockstep. Now, the idea of exploiting data parallelism with acceleration is a very old idea. And some of the original supercomputers were based on this idea. It's called vector processing. But vector processing had trouble making its way into the mainstream because of the stack, because it had a different hardware-software interface, which was challenging for compilers and programmers and applications to take advantage of. It required a PhD to make the best use of these high-performance vector processors. Essentially, what I think, personally, one of the key innovations of GPUs is that they have hidden that complexity, and they expose a different abstraction to software, which is easier to manipulate and use, namely the notion of many parallel threads. And if you can write code where you have all those threads doing different things, it just won't execute very efficiently. To get the best performance out of a GPU, you really want to orchestrate those threads so they're working on doing similar operations. And the GPU, the microarchitecture, takes care of dynamically aggregating those threads and those workers and getting them going in lockstep to get really great performance and efficiency. So I think that's one thing that makes GPUs different from CPUs. Now, there are many things that GPUs are good at that CPUs are not good at, or apps processors are not good at. But there's also many things that apps processors are good at that a graphics processor would not be good at. which is why modern smartphone and system-on-chip embedded systems have both. And this creates heterogeneity. Now, for a long time, I actually was I was very much a proponent of homogeneity, because if I have a homogeneous substrate, it makes it much easier to reason about, both in terms of the hardware and the software. But it's becoming increasingly clear that we're not going to have a homogeneous future. It's going to be heterogeneous. And on one hand, this creates tremendous challenges, but I also think it creates tremendous opportunities. And with challenges comes opportunities for students that are studying in this field in terms of how we manage this heterogeneity, whether it be in terms of software, whether it be in terms of hardware, or whether it be in terms of the new hardware-software abstractions to essentially manage this heterogeneity.
So what forthcoming trends do you see in the field and the future challenges that are facing computer architects?
So I think the single biggest challenge facing architects, which should be keeping the entire semiconductor industry up all night, is essentially the inevitable end of Moore's Law. So Moore's Law says that every 18 to 24 months, the number of transistors per die will double. And for a long time, the entire field has basically ridden this technology scaling. Yes, architects make tremendous contributions in terms of microarchitecture, in terms of the instruction set design, in terms of how to expose this to software. But a lot of the benefit really comes from the fact that in 2 years, I can put more transistors on a die. Those transistors get faster, and to first order, the power density doesn't get too much worse. So I can get, and the cost stays about the same too. But within the next decade, I think it's becoming increasingly clear that that technology scaling will either stop or slow tremendously. And it just has to do with physics. We're getting now to the point where we measure transistors in 100 atoms. And we're just going to run out of space. And they're not going to look like transistors. They're going to look like quantum devices. So on one hand, this is a very scary situation because now we have this kind of impending end of this technology scaling. But on the other hand, it's a tremendous time to be a computer architect, because I imagine in the future, architects are really going to be the only game in town. You're going to have a potpourri of different technologies. You're going to have maybe molecular computing, different type of semiconductors, maybe a little quantum computing in terms of high performance computing. You have this potpourri of different types of technologies. But I don't see anything coming in and replacing silicon CMOS. And it's kind of analogous to how right now if I want to build a new building, I am sure I could go to material scientists and they could talk to me about exotic polymers that have so many benefits compared to steel and concrete. Yet what do I use to build a building? Steel and concrete. Because that's what the infrastructure is developed, that's what everybody knows how to use, and that's the kind of the best materials broadly. I think it'll be the same thing. So silicon CMOS technology will be the standard. There might be some potpourris of different technologies. And so what will really differentiate one system from another system is not the technology, but what you do with it. And who decides what we do with the technology? Architects. Architects are the ones that differentiate one chip from another chip in a given technology node. So architects will become the only game in town. And architects will have a much bigger role in terms of designing future chips. I can almost see a resurgence in terms of chip design startups and basically an emphasis on new types of chips that basically exploit, whether it be applications in specific ways, classes of applications, new types of accelerators. So I think that makes it a particularly exciting time to study the field of computer architecture specifically and more broadly computer engineering.
Professor Christopher Batten from Cornell University. Chris, thanks for joining us.
It was a pleasure. Thank you for having me.